And we're going to wait, Tony, a couple of more minutes because people are finishing lectures, and
sure, yes.
And there is a phase transition changing between virtual rooms.
Yeah, right. So, are you actually conducting lectures in person now?
Not at the moment. Everything is virtual via Zoom and other media.
Yes.
And I'm not sure what is going to happen next trimester. I think we are going to still be doing lectures via Zoom.
Yes. I believe here at UIUC, all lectures have to be in the fall. All lectures have to be offered in person, but there is also arrangements for people to follow them remotely.
I see. And are you currently teaching?
I'm retired, technically.
I see.
It doesn't seem to mean I'm any less busy than I was, but technically I am retired.
But you can teach if you want, no?
I probably could. I have not so far been asked to particularly. Yeah.
I see.
And actually, I do think that I have sufficient other commitments that it might be a bit difficult.
Sure, I see. So I think if it's okay with everybody, also with Tony, I'm going to start.
Okay.
So welcome everybody to Iztapalapa, to Mexico City, virtually of course. My name is Isaac Perez Castillo, and I'm the organizer of the seminar series of complex systems at the Department of Physics at the Universidad Autónoma Metropolitana Casa Abierta al Tiempo. As you may remember, during this first season, we have had the opportunity to enjoy listening to many towering scientific figures from different areas of physics. And today, with the help of Ivan Pompa and David Hernandez, organizers of our seminar series of our graduate program, I thought it would be appropriate to close this seminar series before summer break with another brilliant scientist, Nobel laureate Tony Leggett. So please let me very briefly introduce the speaker of today. Sir Anthony James Leggett, born in Camberwell, South London, is a theoretical physicist and professor emeritus at the University of Illinois at Urbana-Champaign. Professor Leggett is widely recognized as a world leader in the theory of low temperature physics, and his pioneering work on superfluidity was recognized by the 2003 Nobel Prize in Physics. He has shaped theoretical understanding of normal and superfluid helium liquids and strongly coupled superfluid. He set directions for research in quantum physics of macroscopic dissipative systems and used condensed systems to test the foundations of quantum mechanics. Regarding his graduate studies, I would like to briefly mention that he went to Balliol College, Oxford, in 1954 to start doing a degree in classics. And after that, after completing his first degree in classics, he did a second degree, this time in physics, at Merton College, Oxford, under the supervision of Dirk der Haar. His tentatively assigned thesis topic was some problems in the theory of many body systems, which left him a considerable latitude to pursue a wide research of wide areas of interest. Professor Leggett spent a period of 1 year from August of 1964 to August 1965 as a postdoctoral research fellow, at the University of Illinois at Urbana-Champaign, surrounded by prominent figures such as David Pines, John Bardeen, Gordon Bain, and Leo Kadanov. He then spent a year in the group of Professor Takeo Matsuhara at Kyoto University in Japan, and after one more postdoctoral year, spending some time between Oxford, Harvard, and Illinois, he took up a lectureship at the University of Sussex, where he spent the majority of the next 15 years of his career. And also during that time, he spent some time in Japan at the University of Tokyo, and also the Kwame Nkrumah University of Science and Technology in Kumasi, Ghana. In the early 1982, he accepted an offer from the University of Illinois at Urbana-Champaign to take the MacArthur Chair. He arrived at Urbana sometime in 1983, and he has been there ever since. Of course, as you know very well, regarding his awards and honors, Professor Leggett is a member of the National Academy of Sciences, the American Philosophical Society, the American Academy of Arts and Sciences, the Russia Academy of Sciences, the Indian National Science Academy. He is also a fellow of the Royal Society. He's a fellow of the American Physical Society, the American Institute of Physics, and a life fellow of the Institute of Physics. And of course, as you know very well, he was awarded the 2003 Nobel Prize in Physics, together with Gisborne and Brikosov for pioneering contributions to the theory of superconductors and superfluids. He's also an honorary fellow of the Institute of Physics, and he was appointed Knight Commander of the Order of the British Empire in the 2004 Queen's Birthday Honors for services to physics. Of course, he has also many prizes, but maybe we should let the speaker of today give his seminar. So, Professor Tony Leggett, Tony, it's a great honor to have you with us today. The floor is yours, so please take it away.
Thank you. Well, thank you, Isaac, for that very kind introduction. The talk I'm going to give you today is roughly what I gave at the Nobel ceremonies in Stockholm in 2003, though I have updated a little in places. So let's start with some prehistory. Helium comes in the form of two stable isotopic species. There's helium-4, which is relatively common, and helium-3, which has actually only existed in any quantity on Earth in the last 50 years or so, because of oddly enough, nuclear weapons. When a nuclear weapon decays, the tritium decays into helium-3, and that is actually the source of much of our helium-3 here on Earth. Anyway, it's been known for a long time, since the late 30s, that the isotope helium-4, the more common isotope, becomes superfluid below about 2 degrees Kelvin, 2 degrees absolute. But what about the less common species, helium-3? This actually is believed to be a fermion. I'll explain in a moment what that means. And it has this in common with the electrons in metals. Electrons in metals, of course, have been at least implicitly known since ancient times, and they are obviously electrically charged. Helium-3 has only been around since about 1950 and is electrically neutral. However, they do have in common that they're both particles of the electrons and metals and the atoms of liquid helium-3 are both particles of spin 1/2 and therefore obey so-called Fermi statistics. And what this means is that at any given temperature, if you plot the number of particles per state as a function of the energy of that state, it's really pretty boring. The lowest energy states are all occupied with 1 electron per site. Fermions, that's particles of spin 1/2, are very xenophobic. They hate to, in fact, they won't tolerate having more than 1 particle per state. And so you do put 1 particle in all the lowest energy states until you get up to an energy when you've basically accommodated all or most of the particles, and that energy is called the Fermi Energy. And so the distribution has a little structure, as you see from the picture, around that point, but most of the electrons are really not doing anything particularly interesting. So that's the picture which we've had for a long time for the non-interacting gas fermions, and that does seem to describe, rather surprisingly, that seems to describe the state of electrons in metals down to, let us say, 20 degrees absolute, and helium-3 down to a few milledegrees. It was a bit of a puzzle that it was that simple non-interacting picture worked so well. And some light was shed on this by Landau in his theory of a degenerate Fermi liquid. And basically Landau pointed out that in the normal phase at least, interactions don't really change the picture qualitatively. They make some quantitative changes, but basically the behavior of a degenerate Fermi liquid, even with strong interactions, is pretty similar to that of a non-interacting Fermi gas. So it wasn't any mystery then that liquid helium-3 did seem to be behaving qualitatively much like a non-interacting Fermi gas. That is, colloquially speaking, according to the picture shown. However, it's known that the electrons in metals, which have a Fermi temperature of somewhere between 10 to the 4 and 10 to the 5 degrees Kelvin, some metals below about 20 degrees Kelvin show superconductivity. That is essentially, crudely speaking, the ability to carry electrical current without any voltage imposed. And so people began to speculate that in helium-3, where the Fermi temperature is much lower, it's about 5 degrees absolute, if you went to a low enough temperature, say about 10 to the minus 3 K, roughly correspondingly to metals, then you might find, well, you would not find superconductivity because that requires the electrons to be electrically charged. And the helium-3 atoms are not charged, but you might find a related phenomenon, superfluidity, which would be qualitatively similar to the superfluidity in helium-4. Okay, next slide, please. Yeah, so superconductivity has been around experimentally now for more than 100 years. And there have been some very interesting and important theories of what's going on there. The first real theory of superconductivity, which enabled one to actually do anything quantitative, was a phenomenological theory due to Ginzburg, Landau, Abrikosov, and others in the years between 1950 and 1955. And that relied on the idea of a macroscopic wave function. Ginzburg and Landau called the wave function of a superconductor a macroscopic wave function, but they never really explained what they meant by macroscopic, and I'm not even sure they themselves really understood what they meant by it. But we'll see later that, in fact, we do know nowadays, in some sense, what it means. This, however, was a phenomenological theory. In 1957, my former colleagues, Bardeen, Cooper, and Schrieffer, at the University of Illinois in Urbana-Champaign, where I've been for the last 30 years, they produced a microscopic theory of superconductivity. And the crucial ingredient, a qualitative ingredient in that theory was the idea that electrons in a little shell very close to the Fermi energy, with around Boltzmann's constant times the transition temperature, that's very, very small compared to the Fermi energy itself. So you're talking about a very small shell of energy right at the top of the distribution. These electrons would form what are nowadays called Cooper pairs. Now, it's tempting to think of Cooper pairs as like molecules formed of two electrons. And in some sense that's right, but one thing you really have to remember is that the two electrons which form a Cooper pair are very far apart, typically they're something like 10 to the 3 angstroms apart. And so between them, there are any number of other electrons forming their own Cooper pairs. It's a very highly collective phenomenon. And one very crucial feature of the BCS theory, that is the theory of Bardeen and co-workers, is that all Cooper pairs, once they're formed, must behave in exactly the same way. And now it turns out that the so-called macroscopic wave function of Ginzburg and Landau is just the common center of mass wave function of all the Cooper pairs. And the sense in which it's macroscopic is that you have a macroscopic number of pairs occupying that pair wave function. Now, it's interesting that the fact that the electrons themselves are fermions and therefore extremely xenophobic doesn't actually work too much against this, because two electrons, when you put them together, form a so-called boson, and bosons, as distinct from fermions, are extremely gregarious. So they love to all have the same macroscopic wave function. So, and one can actually make that idea more quantitative. It does work, in fact. However, the Ginzburg-Landau theory really only dealt with the behavior of the center of mass of the pairs. In the context of this lecture, I'm going to be much more interested in the internal wave function of the pairs, that is if you like, the relative wave function of the two electrons which are forming the pair. In BCS theory, that internal wave function is rather trivial. In technical language, it's so-called 1s0 state. So that means that the wave function of two electrons forming the Cooper pair is a spin singlet wave function, the standard form, multiplied by an orbital wave function which is spherically symmetric, corresponding to 0 relative angular momentum of the pair. So what that means is that the Cooper pairs in a standard superconductor have no internal or orientational degrees of freedom. There's essentially nothing interesting going on as regards the internal wave function. Next slide, please. Okay, now once helium-3 had been obtained in reasonably in large quantities, enough for experiments, and people had realized that at temperatures of the order of 1 degree or so, it was behaving pretty much like the electrons in a normal metal. They started asking themselves, well, could something like Cooper pairing occur in liquid helium-3? And then they immediately realized within a couple of years that there's actually an important difference between the electrons in metals and the atoms in helium-3, quite apart from the fact that one is charged and the other is not. The electrons in metals do have a repulsion at short distances, the standard Coulomb repulsion, but in some sense the Coulomb interaction is it just increases as 1 over the distance, and it really is in some sense rather mild. By comparison, the two atoms of helium-3, or for that matter helium-4, have a very strong hard core repulsion. It's almost impossible to bring them together closer than a sort of atomic radius, which is something like 3 angstroms, 2 or 3 angstroms. And it's only when you get to distances beyond that short distance that you find there is, in fact, a small van der Waals attraction, which, however, is rather weak. And so if you're going to form your Cooper pairs, you'd better form them so that the distance of closest approach is something of the order of this R0, something like 3 angstroms. On the other hand, you have to form them for pairs near the Fermi energy. And that means that the momentum has got to be of the order of the Fermi momentum, that is the momentum corresponding to Fermi energy. And if you put those together, you find that the angular momentum, which in is basically the product of the Fermi momentum and the distance closest approach, R0, in units of h bar. That cannot be zero, because they can't get arbitrarily close together. So it must be something. Well, people thought probably 1 or possibly 2. And now this is rather interesting, because depending on whether L really was 2, which is an even number, or well, say 1, which is an odd number, the orbital, the spin wave function is going to be different. This is because of the Pauli principle, which says that the total wave function of 2 fermions has to be antisymmetric. So what that leads to is that that if you have orbital angular momentum 0, which is or 2, say, which was one of the possibilities contemplated for helium-3, then you form the spins in a singlet state. But if it were odd, so if it were 1, which is another possibility, then the total spin would have to be 1. In other words, you have a triplet state. But in either case, in either of these cases, if L is not equal to 0, then that means you have a relative or internal wave function of the pair. In other words, the pair has an orientational degree of freedom. And that's a very crucial difference from the Cooper pairs that form in superconductors, and that was realized way back as early as about 1960. Now, a very important couple of papers in the early 60s. One was by Anderson and Morel in 1961. They actually explored in detail the case L equals 2, which was thought at that time to be the most probable case. And incidentally, that exploration has turned out, in retrospect, to be rather useful in the context of the cuprate superconductors. But they also explored a special case of pairing with L equals 1. And that special case is where only up-up and down-down pairs form, which is not the only possibility, as we'll see, and they have the same orbital angular momentum in some direction L. Now, I'm not clear whether, and I've actually asked Phil Anderson this question more than once and never got a straight answer. I'm not clear whether they chose that particular state for any particular reason, or whether it was just that it might look like the simplest state to consider. But anyway, they did analyze its properties in some detail. And that property, as we'll see, has played a role later and is nowadays known as the Anderson-Brinkmann-Morel or ABM state. The physical states, the physical properties of this state are anisotropic, both in orbital and in spin space. A second very important observation was actually made first by a Russian physicist who's not terribly well known in the helium field, named Yuri Vdovin. He's actually mainly a plasma physicist. But he actually did make this observation, which was later rediscovered by Balian and Wertheimer in the US. In the L equals 1 case, you don't have to just consider up, up, and down, down. You can actually consider the third component, which corresponds to total spin 1, but projection z, Sz equals 0. And you can actually form Cooper pairs with all those 3 spin components, and if you do it right, you find that the vector angular momentum for any pair is just opposite to the vector spin angular momentum, and so the total J, L plus S, is 0. And that's what's called the Balian-Wertheimer state, since Dovin's work was not widely known at the time he did it. All the physical properties of this state are isotropic, as you might guess from the fact that J is equal to 0. And what both Dovin and Balian and Wertheimer showed was that if you did have pairing with L equals 1, then the BW state would be more stable than any ESP. That's state. An ESP state is one where you only have up and down pairs, like the ABM state. So around, say, 1964, when I first got into the game, the theoretical expectation was that yeah, it's indeed possible that liquid helium-3 may form Cooper pairs, and it wasn't entirely clear whether they would form with L equals even, and therefore spin singlet, or with L equals odd, in which case you ought to get the Balayan-Wertheimer state. In either state, though, the spin susceptibility should be reduced, and it's obviously reduced in the spin singlet state, just as happens in superconductors. The reason it's reduced in the Balayan-Wertheimer state is that although the up and down spins can react to a magnetic field, just as in the normal state, the SZ equals 0, that's the third component, the up-down plus down-up, can't. It behaves more like a singlet. So in either case, chi would be reduced, and all the magnetic properties would be isotropic. The people, of course, did try to calculate what the transition temperature would be, and crudely speaking, what tended to happen in those days, we're talking now about the mid-60s, let's say, is that the theorists would predict a transition temperature which was just a little below, perhaps by a factor of 2, the lowest temperature the experimentalists have got to. The experimentalists would then go down that much in temperature, and they wouldn't find any evidence for Cooper pairing, whereupon the theorists would go back and redo their calculations and set the predicted transition temperature again a bit lower, just a bit lower than the experimentalists have got to. Anyway, so this provided, of course, a nice incentive for the experimentalists to keep trying to push the temperature lower. However, if I remember correctly, I haven't really checked this up recently, but in sometime around I think the spring of 1972, there came out a theoretical paper which actually redid the calculation a bit more carefully than people had done previously, and they actually predicted a transition temperature of something like 10 to the minus 17 degrees, which was way beyond, of course, anything the experimentalists could ever get to. Luckily, I don't think too many experimentalists read that paper, so it didn't slow them down too much. Anyway, next slide, please. Yeah. So now we come to the interesting bit, as it were. In 1971 to 2, Doug Osheroff, Bob Richardson, and Dave Lee were doing experiments on a mixture of liquid and solid helium-3. As a matter of fact, I think their original motivation for doing these experiments was to look for a magnetic phase transition in the solid. But in order to cool the solid, they used Pomerantz cooling, which requires a mixture of solid and liquid helium-3. So they had this mixture, and the only thing that could actually vary was the temperature, but then they could measure also the pressure. So these first experiments, which if I recall correctly, were done in 71 and the fall of 72, they measured the pressurization, P, as a function of time. And it was Doug Osheroff who actually was doing these experiments in the basement at Cornell. And some night in, I think, October or November of 1972, he actually found a couple of glitches in his pressurization curve. The glitches were very small, but nevertheless, they were large enough to be significant. And what Doug inferred, and what we now confirm, is that either the liquid or the solid, or both, were undergoing not one, but 2 phase transitions. The first transition was at about 2.65 milli-K. That's a second order phase transition. And that was from the normal phase into, well, what is now called the A phase. A second phase transition occurred at a lower temperature of about 2 milledegrees absolute. And this is a first order phase transition out of the A phase and into what we now call the B phase. Well, this is sort of ambiguous, and at first sight, they thought the most obvious explanation for this was a phase transition in the solid, which was in fact what they started to look for. However, shortly after that, joined by Willie Gully, they did a set of nuclear magnetic resonance experiments, again on the mixture of the liquid and the solid. And what they measured is standard NMR experiment. You have a fixed, a constant external field along the z-axis, as indicated. You have an RF field which is transverse to the fixed field. And basically what you do is that you vary the frequency of the RF field, and you measure the absorption as a function of frequency. And from the absorption, you can then integrate that to get the susceptibility. There's a well-known sum model for it. Now, the first thing that they actually found, which I haven't listed here, was that, in fact, the phase transition was not going on in the solid, but in the liquid. And that seemed quite unambiguous from the shape of their curves. So that was the first interesting result. The second result was that was concerned with both the susceptibility and the NMR resonant frequency. In the normal state, the susceptibility was independent of temperature, as Landau theory says it should be. Its value was just as expected from degenerate Fermi liquid theory. So nothing particularly surprising about that. And what about the absorption? The NMR absorption, well, that shows a very sharp peak at the free atom Larmor frequency, which is just the gyromagnetic ratio of the free helium-3 atom times the external field. And that is about 3000 Hertz per Gauss. So the resonance frequency just scaled with the external field, as indeed straightforward NMR theory says it should. However, when you get into get below these two phase transitions, something much more interesting happens. Next slide, please. Yeah, thank you. What happens to the susceptibility? Well, in the A phase, it looks as if it's simply the same as in the normal phase. As a matter of fact, we now know that isn't exactly true, but the difference is very, very slight. So essentially, the A phase susceptibility is just the normal phase one. In the B phase, the susceptibility drops discontinuously and then continues to decrease. That's not particularly mysterious in view of the existing theory. For example, this would be consistent with the A phase being a so-called equal spin pairing phase, with only the up-up and down-down pairs formed, so there was no reduction in chi. Whereas the B phase could be either a spin singlet or the Balian-Wertheimer phase, when, as we already saw, chi should be reduced. The only slight puzzle is why is any ESP phase ever stable? Because as we've seen, both Darwin and Balian and Wertheimer had shown that, in fact, the Balian-Wertheimer phase will always be more stable than that. In other words, you'd expect that the system just went straight from the normal phase into the B phase by a second order transition, but that clearly is not what's happening. But what is really puzzling is the resonance frequency. The resonance frequency stays very sharp, and that's a very important observation, as you go from the normal phase into the A phase. And in the A phase, it starts to shift away from the normal phase Larmor frequency in an upward direction. but it does not shift proportional to the external field. What happens is you get a so-called Pythagorean formula. The square of the resonance frequency is the sum of the squares of the original normal frequency plus some other frequency squared, which appears to be a function of temperature. And if we actually, just from the experimental data, figure out what the that dependency is, we see that this extra term goes as a constant times 1 minus t over ta, roughly, and the constant a is about 5 times 10 to the 10 hertz. Now, how could that happen? Let's first think of the most obvious suggestion. Since the two terms appear to be adding not linearly but according to Pythagoras, the natural assumption would seem to be that somehow the system manages to generate a field H0 which is perpendicular to the external field, and so the total field is just the Pythagorean combination of the two, and that will give you the resonance frequency which you see experimentally. The problem, however, how large does this transverse field have to be? Well, it turns out that to fit the experimental data, you need that H0 is about 30 Gauss. Where on earth could that 30 Gauss field come from? Helium is a very, very pure substance. It's impossible, just about impossible to get any kind of impurities, whatever, into it at millidegree temperatures. So it doesn't seem very plausible that there were any magnetic impurities floating around. So the only apparent source of an extra field, which would be spin non-conserving, which is what you need, is the nuclear dipole-dipole interaction. And then you do a back of envelope calculation, and you remember that these helium-3 atoms can never get closer to one another than about the atomic hardcore radius, which is about 2 or 3 angstroms. And at that separation, the maximum associated field is less than 1 Gauss. And you might think of all sorts of fancy ways of packing the various atoms together so as to get a slightly bigger field than that. But it really turns out that that really doesn't work at all. So this is a real puzzle. Now, at that particular point in time, we're talking now about, I guess, June of 1973, I had been intending for some time to actually stop doing low temperature physics and go away and think about the foundations of quantum mechanics. But when I really started tossing this over in my mind, it seemed to me that this experimental result was so bizarre and unexpected that maybe it was an indication that under these very extreme conditions of not only very low temperatures, unprecedented low temperatures in fact in bulk matter, but also a very, very dense matter and so on and so forth, quantum mechanics itself might actually break down. And so what I did was very specifically and self-consciously, I set out to try to construct a proof that if standard quantum mechanics and standard statistical mechanics were working as advertised, then this experimental result just could not occur. So in other words, something really fundamental must have gone wrong. Well, because as you probably know, it didn't quite work out that way. Next slide, please. There was a vast bulk of existing literature on NMR. I didn't know it. And my first resolution was that I was not going to find out about it, because it was clear that this, at least as far as I knew at the time, this result was totally unprecedented and corresponded to like nothing that had been seen previously in bulk matter. That actually turns out not to be quite true, and I might come back to that later, but that was what I thought. So I had to basically start off from scratch. Now, I was starting from scratch. I wanted to prove a rigorous theorem, say that if quantum mechanics was right, standard statistical mechanics was right, you could not get this result. So how do you prove something exact and quantitative in a system as complicated as a set of helium-3 atoms? Well, there is one way of proving, at least to an extent, exact results known in many body physics, and that is sum rules. So my first thought was, okay, how do I, what can I actually get out of sum rules for this problem? It actually turns out I get something rather interesting. If I made the assumption, and this is an assumption, but it's based on the experiment, I make an assumption that you still, even in the A and B phases, only had a single sharp resonance, then then you would in fact find a formula for the resonance frequency, which is indeed a Pythagorean formula of the type which is observed experimentally. And moreover, that extra term in the Pythagorean formula is given, apart from a factor of gamma squared chi to the -1, it's given by the second derivative of the nuclear dipole energy with respect to a simultaneous rotation of all the spins. But then there are some hand-waving arguments, or fairly convincing arguments, which show that the second derivative with respect to the angle had to be of the same order of magnitude as the equilibrium nuclear dipole-dipole moment itself. So from the experimental value of this extra Pythagorean term, we conclude that the expectation value of the dipole energy in the A phase had to be some constant k times 1 minus T over Ta, and k had to be something like 10 to the minus 3 ergs per centimeter cubed. Now, that doesn't sound very much, and indeed, when you compare it to the energy, say, I don't know, say the other bulk energies in helium-3, it really is very tiny. Nevertheless, there is a very serious difficulty. Suppose that you have two nuclear spins on two different atoms, and they are in some kind of orbital configuration relative to one another. Then the nuclear dipole-dipole energy is going to depend on how they're oriented relative to one another. For this purpose, you could just think of the nuclear spins as just like little magnets, and those of you who've played around with little bar magnets in the lab know how they behave. If you try to set them parallel and side by side, they don't like it at all. That's a bad, that is high energy configuration. On the other hand, if you set them end to end, they like it. That's good. That's a lower energy state. And so if you now translate this into dynamics, as it were, it's much preferable for those two spins to tumble end over end rather than tumbling side by side around one another. Well, fair enough. So there is some tendency for these spins to orient perpendicular to their relative angular momentum. But how strong is that tendency? This is where you really get to trouble. The maximum interaction energy at distance, even at the distance closest to approach, is still only about 10 to the minus 7 degrees Kelvin. And remember that although we're at low temperatures, the temperature is still several orders of magnitude greater than 10 to the minus 7. It's more like 10 to the minus 3. So what this would say then is that the preference for the good orientation over the bad one is very weak. It's at most of the order of the energy advantage relative to kT. And that's only of the order of 10 to the minus 4. As a matter of fact, it turns out for technical reasons, you should actually use not T, but the Fermi temperature, and then it becomes even smaller. But anyway, so the expectation value of the dipole energy on this simple picture is far, far too small. And this is what really puzzled me, and I lay in bed for, I think, 3 weeks at night, trying to lie awake, trying to think how on earth this could happen. And finally, it occurred to me there was a way it could happen. And let's go to the next slide for that. So what I came up with was an idea which I called rather clumsily spontaneously broken spin orbit symmetry, SBSOS. And to explain this, this mechanism, let me take an analogy. The analogy is with a ferromagnetic material. In a ferromagnet, we have a whole set of electrons which have small spins which carry magnetic moments. So there are two terms, or two important terms, in the Hamiltonian of this system. There's a term which has only to do with the interaction of the electrons with one another. And that we'll call H sub 0, and that is invariant under the simultaneous rotation of all spins. And there's the second term, the Zeeman term, and that's given by the next formula down. So that's H sub Z. If you go to perhaps the next, H sub Z is minus mu sub B. Yeah, that's right. Yeah. And you see that breaks the spin rotation symmetry. It tries to orient the spins parallel to the external field. Now, in the paramagnetic phase, when T is above the Curie temperature, the spins will basically behave independently, and the thermal energy will compete with the Zeeman energy. And that means that the degree of polarization will be the degree to which orientation of a given spin along the magnetic field rather than opposed to it is favored. That polarization is going to be of the order of the Zeeman energy divided by the thermal energy, which is much less than 1 typically. And that means the expectation value of the Zeeman energy is going to be N times the Zeeman energy squared divided by kT. So far, so good. Now, what happens when I go below the Curie temperature into the ferromagnetic phase? Well, what happens is that the H0, although it's invariant under rotation of all the spins simultaneously, what it does is to force all the spins to lie parallel to one another. And that's crucial, because what that now means is that to work out the polarization, you have to compare a state in which all the spins, or most of them, are lying parallel to the external field, and one in which they're all lying antiparallel. And the energy difference of those two states is not the Zeeman energy, the single particle Zeeman energy, maybe times h, but rather the that multiplied by n. And n times the Zeeman energy is much larger than kT. So as a result, you get an almost perfect polarization. Almost all the spins line up parallel to the field rather than antiparallel. And as a result, the expectation value of the Zeeman energy is now macroscopic. It's of order, well, it's order n mu bh rather than n mu bh squared over kT, as it was in the paramagnetic phase. So that's something we've understood for a long time. Now let's try to make an analogy in the case of helium-3. In the case of helium-3, what we have is a large term, H0, which is invariant under relative rotation of the spin and orbital coordinate systems. And then we have H sub d, which is the dipole-dipole interaction term. And very crudely speaking, that's that's fine. Yeah, it's given by this expression here, And what I want you to focus on is the fact that that does depend on the orientation of the spins relative to the orbital coordinates, and therefore, if you slightly rewrite it, relative to the orbital angular momentum. Now, in the normal phase, at temperatures, say, of the order of a degree or a few hundred milledegrees, the spins basically behave independently, and so pairs of spins also behave independently. And so, by the argument I already gave you, the polarization is of the order of this G sub d, which divided by kt, and that, as we already saw, is very tiny compared to 1, and therefore the expectation value of h, which has another factor of G sub d in it, is of order minus n G sub d squared over kt, and that is very tiny. In fact, it's so tiny that it's only fairly recently that people have been able to measure that effect in the normal phase. But now suppose we go into the ordered phase below T sub A. Then what we can imagine, and this is a conjecture at this stage, what we can imagine is that H sub 0 will force all the pairs, not all single particles now, but all the pairs of particles to behave similarly. So now kt will be competing not with G sub d, the single pair orientation energy, but with n times that. And therefore, the expectation value of the dipole energy can be of the order, or not of G sub d, but of n sub G sub, not of order n gd squared over kt as it was in the normal phase, but rather n times gd, just of the order of 10 to the minus 3 ergs per cubic centimeter, what's needed to explain the experimental resonance shift. So that at least was quite satisfying. Next slide, please. Yeah, just a note on SPSOS. It's actually quite a subtle form of ordering, as we can see by comparing it with the behavior of a ferromagnet. In a ferromagnet, you only have one type of spins. That's the angular momentum, rather. That is the intrinsic electron spin. In the normal phase, the spins are completely disordered. And now if we go down to the ordered phase, they all tend to line up parallel. But now in the case of helium-3, it gets slightly more subtle. In helium-3, you have two different kinds of angular momentum, the spin angular momentum of a pair and its orbital angular momentum. So I denote the spins by red arrows and the orbital angular momentum by green arrows. And so in the normal phase, you see, first of all, the red arrows are completely oriented at random. The green arrows are completely oriented at random, but there's something else. The relative orientation of the green and red arrows is also random in the normal phase. Now, if we go into the ordered phase, in particular the B phase, it turns out that the spins are still completely random. The orbital angular momentum is still completely random, but the relative orientation of the spins and orbital angular momenta is always the same. It's always this angle of rotation around the particular axis. So yeah, if we can just go a little further down. Yep. So in the case of the ferromagnet, in the ordered phase, we have the simple situation, the total spin polarization is non-zero. In the B phase of helium-3, what you find is that the average value of the spin is 0, the average value of the orbital angular momentum is 0, but the average of the vector cross product, L cross S, is not 0. And that's a very fascinating state of affairs. If we have time, we can explore some of the consequences of that. How am I doing for time? Okay, I'm getting a little close to time, so perhaps I should try to speed up a bit. Okay, so next slide, please. So anyway, that was, well, what that showed was that at least it was not unthinkable that the standard quantum mechanics and standard statistical mechanics, if correctly applied, could give you, at least qualitatively, the magnetic resonance phenomena that you saw that the Cornell group was seeing in helium-3. However, that still left one without a microscopic theory, and moreover, it didn't do anything to resolve the paradox of the two new phases. That is, remember that in BCS theory, the A phase, which is apparently equal spin pairing, that should never have been stable. In fact, experimentally, it certainly is. And this was resolved by a very beautiful idea by Anderson and Brinkman in the spring of 1973. They pointed out there's a crucial difference between Cooper pairing in superconductors and in superfluid liquid helium-3. In a superconductor, the effective interaction, the effective attraction, which forms the Cooper pairs, is due to exchange of a lattice vibration. That's nothing really directly to do with the electrons, it's to do with the ions. So the lattice vibrations themselves are pretty much insensitive to the onset of pairing between the electrons. In other words, so this mechanism of attraction is more or less left unchanged when you go into the superconducting phase. By contrast, in liquid helium-3, it's believed, and this is work which had been done in the mid-60s by various people using a sort of spin polarization idea. People have figured that a lot of the attraction between two helium-3 atoms would come out of spin fluctuations of the helium-3 atom system. But that's a fluctuation of the helium-3 itself. So it's sensitive to the onset of pairing. And this means you can get feedback effects. By forming the pairs, you actually change the mechanism which forms them. And you actually do a quantitative calculation, as Anderson and Brinkman did. And what they found was remarkable. Over most of the phase diagram, indeed, the Balion-Wertheimer state is stable, as in BCS theory. But at hydrogen pressure, feedback effects uniquely favor the ABM phase. And this is a major qualitative leap beyond BCS. And a really new idea, I think, we have learned from the new phases. So at this point, things seem to be in sort of relatively good shape. We had a qualitative, at least qualitative, and even a quantitative idea of which said, okay, the A phase is probably the ABM phase. Theory of the NMR dynamics, and we still many other things we don't understand. Oh dear, am I being heard all right? Because there's a notice which has just appeared saying my internet connection is. I'm okay?
Yeah. You're okay. We lost you for a second, but you are back with us.
Okay, good. Okay, fine. So I guess I ought to probably try to conclude fairly soon, but let me just go on to the next slide, which if I'm not, yeah, okay. I really probably need to skim through this fairly rapidly. This is the microscopic theory of spin dynamics, which I actually formulated a few months later than my original thoughts about spontaneously broken spin orbit symmetry. When I went to Cornell for a month to interact with the experimentalists, and that was incredibly productive. And so I managed to get out a microscopic theory of the spin dynamics. And well, to cut a long story short, the outcome of that was that the linear NMR behavior was completely determined by the eigenvalues of a particular second derivative of the dipole energy with respect to simultaneous twisting of all the spins relative to the orbital angular momenta. And so that allowed us to fingerprint the A and B phases by NMR, and the upshot is that we could unambiguously identify the A phase as the ABM phase, which is indeed what Anderson and Brinkman had postulated. And moreover, we can identify the B phase as the BW phase, at least as regards the NMR experiments which had been done up to that point. But there is actually a subtlety in the BW phase. You remember that in the BW phase, the spins are rotated relative to the orbital angular momentum by a particular angle, and it turns out that angle is about 104 degrees, and that usually that rotation is around an axis whose best choice is the external field. Now that actually has a rather peculiar result. It turns out that what that means is that you would not expect any shift in the transverse resonance, which indeed is what's seen experimentally. However, if you do the longitudinal resonance, if you do a longitudinal resonance, which no one had previously done in helium-3, in which you have an RF field parallel to the external field, not perpendicular, then what you'd expect is a finite frequency longitudinal resonance. Also, you'd expect that in the ABM phase, but it's most spectacular in the BW phase. And sure enough, that was found. And I think that pretty much convinced people that the theory of NMR, which I'd worked out, was along the right general lines. So let me just, I think I have one more slide which I can show before I run out of time. So one more slide, please. Yeah. So by the summer of 1973, both a priori considerations and, sorry, I think it should be 1974 actually. I always get my years mixed up actually. But both a priori stability considerations, as Anderson and Brickman, and NMR experimental data, they're consistent with the hypothesis that both new phases are Cooper paired, and therefore presumably superfluid phases. In fact, people started talking about superfluid helium-3 long before there was actually any explicit evidence for superfluidity. There was evidence for Cooper pairing, but no evidence that the resulting pair state would be superfluid. More specifically, we could say by that time that the A phase is very likely the ABM phase, the B phase is very likely the BW phase. So just to very briefly, what is superfluid helium-3 good for? Well, I think it's the most sophisticated, at least until the advent, about 10 years later, of the fractional quantum Hall effect. Superfluid helium-3 was the most sophisticated physical system of which we could claim a detailed quantitative understanding. And all sorts of ideas which were evolved in the helium-3 context were then applied later, for example, to high-temperature superconductors. There are all sorts of analogies which people have tried to exploit with systems of particle physics and cosmology. Griffith Wolovic in particular has emphasized that. You can use it for studies of some important aspects of turbulence. The one I just want to say a brief word about is the amplification of ultra-weak effects. Basically, the NMR behavior is already a manifestation of the amplification of an ultra-weak effect by the phenomenon of Cooper pairing and the fact that the Cooper pairs all have to do the same thing at the same time. So let me take the example of looking for an effect of the neutral current part of the weak interaction, which violates P, parity, but not T, time reversal. You can't get such an effect in a single elementary particle because any electric dipole moment must be proportional to the only characteristic angular momentum, which is J. And that then violates both T and P. However, for helium-3b, you can actually form the product L cross S, and that, amazingly, violates P, but not T. And therefore, you might imagine get a very tiny electric dipole moment along the axis of rotation of S relative to L. Now, let me emphasize, this is a very, very tiny effect. You start off by you start off at the elementary particle level, and then you have to go through the atomic level, through the level of molecular physics, and finally to the level of Cooper pairs. And by the time you've done all that, the magnitude below what one would ever dream of seeing experimentally. However, in the B phase, remember that all the pairs have exactly the same value of L cross S. So you're multiplying that small effect by a factor of about 10 to the 23, and it's still pretty small, but it's not so small that you might despair forever finding it. And indeed, at the time in the mid 70s, I did suggest to a few experimental groups they might look for that, but they eventually decided that they just didn't have the resolution at that time. More recently, one or two groups have become interested again, and I really rather hope that well, at least one group will actually look for this this effect. It would be, I think, the first real evidence for a macroscopic effect of the parity violation which occurs at the level of single elementary particles. And I think that would be really rather cute, but so far no one's done it. Anyway, so the basic message I want to try to put across is that the spectacular effects which you see in helium-3, of which the best known is the NMR, but there are many others, they result from the fact that Cooper pairs are formed and all those Cooper pairs have to behave in exactly the same way at the same time. Thank you. Oh yeah, okay, yes, you can just show those slides. This is a slide of the Nobel medal, and we have the, I think, yes, the certificate. And then finally we have the artist representation of Cooper pairs, which I rather like. They're like
yes. This one, right? Yes.
Yeah, right. Green cherries. I don't think real Cooper pairs or anything like that. But...
So Tony, thank you very much for this fantastic talk. So shall we thank Tony before going to questions? Thank you very much, Tony.
Okay.
So we have time for some questions. So if somebody has some questions, please just raise your hand or unmute your microphone and ask directly to Tony, please. Go ahead. Some questions? Salvador, adelante. Pero tu micrófono, your microphone doesn't work.
Let me see. Okay. Can you hear me now?
Yes, we can.
Yes, I can hear you too.
Professor Leonard, thank you very much for this enlightening lecture, for all the steps you followed and important ideas you devised for explaining this phase transition effects in superheat fluidity and helium-3. I have a question. What do you think about the case of nanodroplets, helium-3 nanodroplets? Do you think still the superfluidity properties are kept at the same level of nano size of these nanofluid droplets?
Yeah, I think that would, my theoretical expectation would be that that would depend rather strongly on the size of the droplets. And I think my first guess would be that you'd have to have a droplet which is at least as large as the pair radius, the radius of the Cooper pairs at that temperature and so forth. And I suspect that most of the nanodroplets which people are looking at experimentally don't satisfy that condition. However, there is a further point, a more complicated point. In a superconductor, it is not actually necessary for existence of the superconducting state that the grain size be large compared to the pair radius. In fact, it can really be much smaller than that, and you can still get a recognizably superconducting state formed. Is that the case with helium-3? Well, the problem is that typically anisotropic superfluids or anisotropic Cooper paired states are much more sensitive to boundary conditions than the ordinary BCS state. So I think my instinct would still be that it's unlikely that you would see much evidence for superfluidity in droplets which are small compared to the pair radius. However, if you can tell me I'm wrong, I'd be very interested.
Oh, no. I was just thinking about this L cross S average value, which perhaps could be size independent, and maybe it could really define some characteristics when you have very small sizes for, let's say, not a bulk type of behavior, but your last slide at the conclusion made me think about this P violation term that you mentioned, and I don't know if I'm not expert in this field, but I just that made me think about these
Yes.
properties.
Well, yes, that's. I think it's sort of a possibility. Again, I think my my instinct would tend to be that the B phase probably will not form as easily in a small droplet as it will in bulk. That seems to be the case when you impose other kinds of boundary conditions. For example, there have been a lot of experiments on helium-3 in both Vicor and aerogel, where you have very severe constraints due to the solid boundaries. And generally speaking, you find that the B phase is not so favored as it is in bulk. But frankly, I haven't kept up with the field of droplets in the last few years, and so I would need to actually go back and look up the orders of magnitude and so forth. As regards this parity violation effect, I'm afraid that it would, even if the B phase does occur in small droplets, it probably would not be very easy to see that effect, because even in bulk, even if I have a sample of the order of several cubic centimeters of helium-3, which is about all that anyone will ever let me acquire these days, I still don't, it's still extremely difficult, perhaps impossible, to see this effect. So I think going to small droplets would probably not be, in that case, the right direction.
Well, thank you very much, Professor Leggett. It has been an honor to listen to your beautiful lecture. Thank you very much.
Thank you.
Thank you, Salvador, and thank you, Tony, for the answer. More questions, colleagues, please raise your hand. So let me see, because I have two computers in front of me. So Sylvia, Celia, if you have a question, please, would you mind to unmute your microphone and ask directly? Is that okay? Can you do it?
Yes. So I thought I couldn't use my microphone. So Professor Leggett, thank you for your fantastic talk. It was fantastic. I do research in MRI imaging things for magnetic resonance. So I know that the Nobel Prize Paul Lauterbur was from the same university. Yeah. So I have a curiosity. There was a relation of research between you two working on this in this area, because the superconductive magnets are very vital for the MRI research.
Yeah, no, actually, I'm afraid I have to say there's really no relation. And in fact, the when I did the particular research which the Nobel Committee eventually recognized, I was actually not at the University of Illinois. I was at the University of Sussex in the UK. I had in fact had a brief stay at the University of Illinois, and I can say that much of my understanding of the theory of superconductivity or superfluidity did derive from that stay. But at that time, Paul Lauterbur was not around.
Okay, thank you.
Okay.
More questions? A couple of more questions before we conclude the seminar of today.
Yes, if may I, Isaac?
Of course, yeah, Adrian, please go ahead. Yes.
Thank you. Thank you very much, Professor Leggett, for this talk. It was very, very nice explanation of this fantastic phenomena. And the question is a little bit technical. I saw this semi-classical equation of motion in the microscopic spin dynamics. Can you just for my education, how you get these equations, what you call semi-classical equation of motion?
Yeah. Well, as a matter of fact, that's historically interesting, because it actually, the way I actually got to that was that I had, when I was a postdoc at the University of Kyoto in Japan in 1965, a few years before this happened, I had actually tried to produce a theory of two-band superconductors. And I had written down a theory which involved the two simple variables. One was the number imbalance between the two bands, and the other was the relative phase of the Cooper pairs of the two bands. At the time, that seemed wasted work because of the experiments on which I based this, which I motivated this calculation, turned out to have been wrong. But I had actually done that calculation. And so, yeah, what you do is to define two quantities. One is the ordinary total spin, which is, of course, the three-dimensional vector. And the other is this quantity, which I would call the spin of the Cooper pairs, but that's a rather subtle concept. It's tempting to think that if I've got so let's say my superfluid is 0 temperature, and it is actually Cooper paired, and so in some sense all the atoms are playing a role in the Cooper pairing. However, if, for example, I put on a magnetic field, I can induce a total spin polarization, and I can also induce a certain value of the Cooper pair spins. But the tricky thing is these two are not the same. If I talk about the spin of the Cooper pairs, it's in some sense a measure of the extent to which the spins which form a Cooper pair are correlated. So I do have to define it quite carefully, and I can do that. In fact, in my original paper, I did that in terms of the second quantized annihilation and creation operators. But the crucial point is that it is not that quantity, which I put capital T. It's also boldface capital T. It's also a vector. It's not the same as the total spin, and they do have an interesting commutation relation. I forget whether I actually wrote down if we could just go back for a moment to the slide in question, which is the microscopic spin dynamics.
Yes.
2 slides back, we could just take a look, and I could see if I actually defined that quantity T in that slide explicitly. Back. Yeah, here we go.
Yes.
Yeah, so I've actually simplified a bit by I've actually chosen not the actual vector T, but rather its direction. So, so I mean, to make this totally intelligible, of course, I would have to write out what exactly I mean by the orientation of the spin of the Cooper pairs. I can do that, but I can't do it in my head, as it were. And it wouldn't make sense to try to do it on this slide. But it is in my original paper.
No, thank you very much. Yes.
Thank you, Adrian, and thank you, Tony. One more question. If nobody has one more question, maybe I have one myself. Otherwise, so then, Tony, let me ask you one question. I love your seminar. It was very clear, particularly because I have to follow and I have to share the presentations. I have to pay very close attention. I was very surprised when you mentioned, because I guess it's important from a historical point of view, that you thought when you look at these experiments that it might be that quantum mechanics broke down at that time. So looking nowadays at the state of the art of modern condensed matter physics, do you have a hint of some experiment or something that may give an idea of some breakdown of quantum mechanics, or now you think that this quantum mechanics is a very robust theory, and maybe our task is now to understand other stuff like collapse of the wave function, etc., etc.
Yeah, well, when I first started, I eventually got back to the foundations of quantum mechanics around 1980, and at that point, I started thinking about experiments which one might do on, for example, superconducting devices to bring the predictions of quantum mechanics much closer to our level of everyday life. And if you had told me at that point in, say, 1980, that people were doing experiments at the level that they're now doing with so-called flux qubits and related things, and asked me to bet on the probability that quantum mechanics would still be working at that scale. I think I've only given you a sort of 50% bet. Now, I guess I have to be a lot more conservative, obviously. But it's only relatively recently that we've been able to do experiments which not only show that everything is consistent with quantum mechanics, but also show, which I think is very important, that the world, as it were, is not consistent with a particular set of hypotheses at the macroscopic level. The idea that at least whatever may happen at the microscopic scale, at the level of superconducting devices and so forth, they are always definitely in one state or the other, and not in some kind of quantum superposition. And so everything is consistent with them, has been consistent for 20 years with them being in a superposition. We've never been able to prove that the opposite cannot be true, and that's something we achieved. At least I claim we achieved about 5 years ago, in fact. So now we know that so-called what I call macro realism is not valid, at least at the level of scripts. What I would like to see is actually some extension of that, this line of research, and in particular, I would love to see a so-called EPR Bell experiment conducted between two astronauts in spaceships separated by more than, let's say, 2 or 3 light seconds.
Sure.
This would really knock out a whole lot of possible interpretations of the collapse postulates and so forth in quantum mechanics.
I see. Tony, I would love to give you more, to ask you more questions, but so let us leave it for another occasion. Okay. So, colleagues, shall we thank Tony for this fantastic talk one more time? Thank you, Tony. So once again, thank you very much, Tony. Thank you very much, all of you, for attending this seminar series. Now it's time for a summer break, so enjoy the holidays. Yes. And see you back in August. Once again, thank you, Tony. Okay. See you all. Bye-bye.
Bye-bye. Bye.
Bye.
Bye. Thank you very much.
Bye-bye. Bye-bye.